end is supported by a cable, and a load of weight 80 newtons is supported at the end of the rod. We are asked to find the tension in the cable and the force of the hinge on the rod. So let's start by visualizing the problem. I'm going to take right as positive x, up as positive y, and counterclockwise rotation as positive. So this system is at a static equilibrium. That means there's no translational motion or rotational motion in the system. So let's draw a free body diagram for the rod. The rod is uniform, so the center of mass is located at the midpoint. That is the weight of the rod, and we have the tension from the cable. It is at an angle of 30 degrees. And then we have the tension force from the string that is connecting the load and the rod, and we know the weight of the load. Let's just take it as WL, the weight of the load, and then the tension force on the string is constant. It doesn't change because same string. This tension force is equal to weight of the load. They are equal in magnitude. The tension force on the string is same throughout the string because the string is massless. Okay, so now if you resolve the tension force from the cable acting on the rod into two components, you have one along the x-axis and the other one along the y-axis. The x component is the cosine term, the y component is the sine term. And then there is another force from the hinge point. You have the x component of the hinge force. I expect it to act in positive x direction because we have the x component of the tension to the left. There should be another force balancing it. And the y component of hinge force, let's assume it's acting up. It could be acting up or down. Let's continue the calculation assuming it's acting up, and if that is not correct, we are going to get a negative value for our y component. So that is the length of the rod, equal to 1 meter, and then the center of mass is at the midpoint of the rod, so that should be 0.5 meters. And then we know the weight of the rod is equal to 80 newtons. No, I'm sorry, it's 28 newtons, and then the angle between the weight and the rod is equal to 90 degrees, and then the weight of the load is 80 newtons, the angle is 90 degrees, and we have specified the coordinates, and we are trying to calculate the tension force. The direction of the tension is given, and the other force is the hinge force. We know that we need to solve for the x and y component of the hinge force, and then we can use Pythagorean theorem to find the resultant, and then we need to find the direction theta and measured in newtons. So let's use Newton's second law in x direction, and then Newton's second law in y direction, and then net torque is equal to I times alpha. This I is the moment of inertia and alpha is the angular acceleration. If you're not familiar with I and alpha, do not worry, because in static equilibrium problems, torque is going to be equal to 0. So alpha is anyway 0, so you don't have to worry about the two terms I and alpha. So net torque is going to be 0 in the system because the system is at a static equilibrium, which means there's no translational motion or rotational motion. So if you look at the free body diagram now, we have assumed the object as a rigid body, and the axis of rotation, I'm going to choose this point as the axis of rotation. Then I do not have to consider the torque from the x and y components of the hinge forces. I just have to consider the torque from the tension force. It's going to create a counterclockwise torque. It's going to rotate your system counterclockwise. So it's going to be a positive torque from the tension of the cable. 1 meters is the distance, theta sine 30, and then the next force that is producing a torque about the axis of rotation is the load. It's going to create a clockwise rotation. From our science, we know that the clockwise torque is negative. So weight of the load times 1 meters is the distance, sine 90 degrees. And then the third force is the weight of the rod. It's going to create a clockwise rotation. It's negative weight of the rod times the distance is 0.5 meters, distance between the axis of rotation and the force, and then angle is 90 degrees. Sine 90 is equal to 1. So when you add all these torques, you should get a 0 because net torque on the system is 0. The system is at a static equilibrium. It's not rotating. So tension force is equal to, I'm going to separate the tension, and weight of the load is 80 newtons times 1 meter plus 28 newtons times 0.5. Divide that by 1 meter. So I'm going to show that 1 meters, if you divide something by 1 meter, it doesn't really change, times sine 30. I use the 1 meters to show you how the meters is going to cancel out. Meters is common for all the terms in the equation. You can cancel out that. You end up of getting your final answer in newtons. So if you solve for the tension force, you will get 188 newtons as we expected. We get newtons for the unit. And the direction is already known. It is acting at 30 degrees above the negative x direction. And let's use Newton's second law in x direction. And we have just two forces acting along the x direction. Do not forget the x component of the tension force. It's acting to the left. T cosine 30. And hinge force is acting to the right, because there should be one force to balance this x component of the tension force. Otherwise, there is going to be a net force in the system, because we only have this negative x component of the tension force and the hinge force acting on the system. So it is equal to the x component of the hinge force, 162.8 newtons, and then all the forces acting in the y direction. Look at the forces. We have weight from the rod, load, and then we have to consider the y component of the tension. Tension sine 30, not cosine. And then the hinge force, the y component of the hinge force. I'm going to assume it's acting up. If that is correct, I'm going to get a positive value for the answer. So let's see. 188 newtons is the, that is the weight of the load plus weight of the rod minus T sine 30 is equal to hinge, y component of the hinge force. And if you substitute the values, 28 newtons plus 80 newtons minus 188 newtons times sine 30, you will get. Give me 1 second. I'm going to do the calculation and let's see what I get. 14 newtons. All right, so that's positive as I expected. The hinge force is the y component of the hinge force is acting up. All right, so now I have the x component of the hinge force acting to the right, y component of the hinge force acting up. So pay attention to the relative magnitudes of the forces. The x component is large when compared to the y component of the hinge force. And I'm going to make the vector triangle with the x and y components, and I'm going to find the magnitude of the resultant force. Using Pythagorean theorem, so I just have to take the square of the x component, then square of the y component, add them together, and then take the square root of it. So this is the hinge force. We have x component squared plus y component squared. So this is equal to 162.8 newtons squared plus 14 newtons squared. And take the square root. You will get 163 newtons for the hinge force if you round it to the three significant figures at. So I'm going to find the angle. We need to use tan theta. You don't have to necessarily use tan theta. You could use sine, cosine, or tan theta because now we know all three sides of our vector triangle. So theta is inverse tan, 14 divided by 162.8. And I get 4.92 degrees. I rounded it off to just three significant figures. And it's above the positive x direction, above horizontal. All right. So is the solution complete? Yes, we calculate the tension from the cable and also we calculate the hinge force. Do not forget to find the direction, guys. That is really important. Not only the magnitude, but also the direction of the hinge force. Very important. And is the solution complete? Yes, the solution is complete. The sign of the answer is correct. And then the answer have correct units. And the magnitude of the answer reasonable. So that would be it.